Okay, elemental composition didn't work. Here's what we had hoped. We had hoped that we take a bronze artifact, figure out its exact elemental composition, that means the percentage of different elements that it has, and go to some copper mine somewhere, and that place would ideally have the exact same percentages of elements in the copper ore. And then you could match these up and say that this thing came from here, for example. But that didn't work. Elemental composition didn't work. Why? Because half the elements melt off. They evaporate out. They're just gone. Or when you add in flux, that changes the percentages. So by the time you finished processing the metal, it's some elements have evaporated, some have been added from flux. So much has gone wrong that the elemental compositions are totally changed. So you can't use elemental composition. You just can't use it to match it because it keeps on changing. So what do we need? We need something that's going to be constant, that's not going to change when you heat it up, or change when you process it, or change when you add flux. So we're looking for something else. And that's where we're going to talk about something pretty crazy called isotopic composition. So what is an isotope? Okay. If you remember from chemistry, I hope you remember from chemistry, that the number of protons in an atom determines what element you have. So for example, if you have one proton, it's hydrogen. If you have one proton and one neutron, one proton and 0 neutrons, one proton and 2 neutrons, it's still hydrogen. If you have 6 protons, that's carbon. Whether you have 6 protons and 6 neutrons or 6 protons and 8 neutrons, it's still carbon. So the number of protons determines the element. But different atoms of a particular element can have different number of neutrons. So for example, carbon can have 6 neutrons, but it can also have 8 neutrons. So you have 2 different, what we call isotopes of carbon. It's still carbon, but it has different isotopes, a different number of neutrons, a different atomic mass. The atomic mass, by the way, is the protons plus the neutrons. The total number of protons plus the total number of neutrons in a given atom's nucleus is the atomic mass of that atom. So here's the amazing thing about isotopic composition. It doesn't change quite as easily as elemental composition. If you have some metallic ore and you heat it up, you melt it down, whatever, elemental composition might change, but the isotopic composition doesn't change. So suppose there's some lead in the ore. Half that lead might vanish, but the actual percentages of the isotope of lead, it's not going to change. Let's see if we can actually use an example here. Here are 4 isotopes of lead. And let's just say that the lead in a particular artifact had the following composition, had the following isotopic composition. 35.46% was lead-204, 22.82% was lead-206, etc. That number is going to be unchanging. Now you might say, well, what if you just remove half the lead? That's fine. But each half is going to have this same isotopic composition. Even if you get rid of 98% of the lead, the remaining 2% of the lead is still going to have this exact isotopic composition. The isotopic composition doesn't change very easily. Isotopes, by the way, we use them a lot. I mean, if you think of, for example, hydrogen, the normal isotope of hydrogen has a proton and no neutrons. Deuterium, that's a 1 proton and 1 neutron, that's used to make something called heavy water. Tritium, that's 1 proton and 2 neutron, that's used for various things that require luminescence. It's also used, interestingly enough, to make hydrogen fusion bombs. Obviously, tritium is the by far most expensive of the various isotopes. So anyway, the amazing thing about isotopic composition is it just doesn't change that easily. You heat it up, you boil, you melt it, whatever. The isotopic composition stays the same, so that lets us more effectively match an artifact to its source.